Okay, in the bonding unit, you have to really do a good job keeping things straight. First of all, there's the between atom kinds of attractions, which we call bonds. And that's like covalent, ionic, and metallic. That's what holds one atom to another within a molecule or within a structure. When we're talking molecules, though, so now we're honing into the covalently bonded type of material where we use the word molecules. We then can say, well, the molecules themselves must attract to each other somehow also. We know this is true because, after all, molecular material like water or carbon dioxide can be in the solid and liquid state. So in order to explain that, you must have to say, well, those molecules have some way of attracting each other. And so, as you recall from early in the course, we had discussed two intermolecular forces, dipole-dipole and van der Waals. Recall that dipole-dipole occurs for polar molecules like water. And again, a polar molecule is one where the electrons were not evenly distributed in the molecule. So you had a place in the molecule where there were more electrons. So that end of the molecule starts to take on a little bit of negatively charged character, and the other side would be sort of positive. And so, of course, then those oppositely charged ends of the molecules attract each other electrically, and that explains how they can hold each other together. The van der Waals force is a very weak force that exists between nonpolar molecules where there really is no asymmetry in electron distribution. It's, again, a very weak force. The force gets larger as the molecule size gets larger. That's about the only thing you have to understand there about van der Waals. So, for example, if I were to compare methane to, say, propane, which is a bigger molecule, I would expect propane to have stronger intermolecular forces than methane. However, if I were comparing methane to water, I would say water would win every time because dipole-dipole attraction is so much stronger an attraction. A special kind of dipole-dipole attraction is hydrogen bonding. You need to figure out the details of that, get into your book and figure that out, but I'll give you a little preview. It involves three highly electronegative elements, but you need to dig into that or talk to your teacher one-on-one on that one. Conceptually now, if we go over here to talk about the effect of all this, the weaker the intermolecular forces are, then you could say, well, it's more easy to get the molecules pulled apart from each other. That would make some sense. A weak attraction between particles means they're easily separated. And so that has several ramifications. One would be that the material would melt easier. If it had a weaker intermolecular force, the particles separate easier. That would say the particles change phase to from solid to liquid easier, and we would therefore expect a property called the heat of fusion to be lower for that material. The same logic could hold true for boiling. The weaker the intermolecular forces, the easier the material, easier time it has boiling, and you would expect the heat of vaporization value to be lower as a result of that. And finally, if the intermolecular forces are weaker, anytime the material is in the liquid state, we would expect it to evaporate more easily. Therefore, the amount of vapors over the liquid would be greater, actually, for a material like this than for one with stronger intermolecular forces. So the vapor pressure value above that solution in a sealed container would be higher. And you can go to table H, which shows some vapor pressure curves there, and kind of see that demonstrated. So you should be able to use table H and figure out which material has the higher or lower intermolecular forces based on the vapor pressures. And you, again, should probably talk to your teacher or attend a little board session on table H.